We have arrived at a strange moment in our history. Right now, machines built by human hands are crawling across the rust-coloured dust of another planet. A spacecraft we designed was deliberately steered into the storms of Saturn and destroyed on purpose because we wanted to know what was down there. Cameras we built photographed the frozen plains of Pluto after 9 years of falling through absolute nothing to get there. From the outside, it looks like we have mastered this. It looks like crossing the void has become ordinary. But that sense of mastery is a comfortable lie. We move with astonishing freedom in one direction, and we hit a wall in the other. There is a place in the sky that should be the cheapest destination of all. It remains, after 70 years of spaceflight, very nearly unreachable. I am talking about going up, about leaving the flat tray where every planet slides in its circle, and looking at our own star not from the side, the way we always have, but from above it. The top and the bottom of the solar system. The one direction we have never travelled. At first hearing, that sounds absurdly easy. If you want to leave a spinning plate, you point the rocket upward and you fire the engines. That is where physics smiles at us, rather coldly. The laws involved do not merely make this trip difficult, they very nearly forbid it. Over the next 20 minutes, you will find out why climbing out of that plane costs more than crossing the entire solar system. What is actually up there in the one region we have never photographed, and how engineers propose to break through the wall, with a manoeuvre in which, to go up, a spacecraft first has to fall towards the sun. But none of it makes sense until you understand why the plane exists at all. Because it was not designed. It is a fossil. 4.5 billion years ago, there was no sun and there were no planets. There was a cold cloud of gas and dust drifting between the stars. And that cloud was turning. Barely at all, but it was turning, because everything in the galaxy is turning. Then something disturbed it. A shockwave from a dying star, most likely. The cloud began to collapse under its own weight, and as it fell, that barely there rotation did what rotation always does when something contracts. It sped up. The same reason a spinning skater accelerates when she pulls her arms in. The cloud was pulling its arms in across trillions of kilometres over millions of years. And a collapsing cloud that spins cannot stay a sphere. Material falling straight down along the axis of rotation meets nothing to stop it and keeps falling. Material falling in from the sides is swung around and caught in orbit, so the sphere flattens. Within a few million years, a shapeless cloud had become a disk, with a new star burning at its centre. Everything we have ever known was assembled inside that plate. Every planet, every moon, every rock that has ever fallen through our sky, condensed from material already orbiting in the same plane, in the same direction. That tidiness in the textbook diagram is not an artist's simplification. It is the frozen record of one cloud's rotation, still turning. So the disk is not a map, it is an inheritance. And we did not simply form inside it, we are still bound by its rules. That ancient spin is still in us, and in everything we build, and it is the reason the vertical is closed. Which brings us to an uncomfortable fact about you personally. At this moment, sitting perfectly still, You are traveling at a brutal speed. The Earth does not hang motionless in space. It races around the Sun at roughly 30 kilometers every second, more than 100,000 kilometers an hour. And you have done it your entire life without once feeling it. Here is the detail that changes everything. Every rocket that has ever lifted off is born already carrying that sideways motion. It leaves the pad with 30 kilometers per second of the cloud's ancient spin already in its pocket, entirely for free. For almost every mission we have flown, this is an enormous gift. When we want to reach Mars or Jupiter or Pluto, that inherited push does nearly all of the work by itself. It is like stepping off a spinning roundabout. You are already flung outward with speed to spare, and all you need is a small nudge in the right direction. But going up is a different problem entirely. Picture the solar system as an enormous vinyl record, turning slowly, with the planets as ants walking across its surface. Traveling from one planet to another is an ant walking towards the edge. Difficult, but the record itself is helping. Going up is the ant trying to leave the record. And to climb perpendicular to everything, you must first cancel the 30 kilometers per second you are already carrying. You have to burn an appalling quantity of fuel simply to stop, to hold still relative to the sun, before you gain any height at all. Engineers measure this with a single number. They call it delta V, the total change in velocity a maneuver demands. That price is paid in fuel, and fuel is mass, and mass is the thing that makes rockets impossible. So compare them honestly. Leaving Earth orbit for Mars asks for roughly 4 kilometers per second. For Pluto, about 8.5. Turning 90 degrees and climbing out of the disk by brute force asks for close to 30. Not 30% more, roughly 3.5 times the price of the longest journey we have ever actually flown, to reach a place that on any map looks as though it is right beside us. That is the cage. The spin of that ancient cloud hands us free passage across the disk in every direction we care to go, and raises a wall the instant we try to leave it. It costs more to reach a point above the Sun's North Pole than to cross the 5 billion kilometers to Pluto. Because that climb is so expensive, almost nothing has ever attempted it, which produces a genuinely embarrassing situation. Here, in 2026, the regions directly above and below our own star remain the least explored territory we have. Not in the galaxy, in our own house. We have maps of Mars detailed enough that planners argue over which crater to land in. We know the volcanoes of Io and the hidden ocean of Europa. But the poles of the Sun, the star heating your skin and holding your planet in place, have barely been looked at. And this is not a matter of pride. It is a matter of consequence. The polar regions are where the Sun's most violent behavior originates. The fastest solar wind pours out from there, at nearly double the speed of the wind leaving the equator. And it is at the poles that the star does the strangest thing it does. Roughly every 11 years, its magnetic field turns completely upside down. North becomes south. The entire magnetic architecture of the Sun reverses, and it begins at the top and the bottom. That process reaches into your life. It governs the solar cycle. It drives the storms that interfere with satellites, scramble navigation, disrupt radio, and in the worst cases, push current through power grids never built to carry it. Forecasting any of it depends on knowing what the poles are doing, and until very recently, we had never properly seen them. Every image of the sun you have seen in your life was taken from near its equator, not by choice, but because Earth sits in the plane, and every telescope we own sits in the plane with it. It is like trying to understand the weather of an entire planet while standing on the equator, never once allowed to travel north. You would learn a great deal. You would build confident theories, and you would have no idea there was ice at the top. In the entire history of spaceflight, only 2 missions have ever climbed high enough to look down on the poles of our star. 2. And the first of them is one of the saddest stories in exploration. It was called Ulysses, launched in 1990, a joint European and American mission built to solve the exact problem we have been describing. Its designers knew no rocket on Earth could cancel 30 kilometers per second by brute force. There still isn't one. So they did something that sounds like a mistake. To go up, they went out. Ulysses was launched away from the Sun entirely, on a long climb to Jupiter, arriving in February 1992. And there it threw itself into the giant planet's gravity, and let Jupiter's enormous mass whip it out of the plane, hurling it back inward on a steep new path that carried it over the Sun's south pole and then, years later, over the north. It was an elegant, patient, deeply clever piece of work. It cost them an extra 4 years and a journey to Jupiter to travel a direction that was, in a sense, already right beside them. And it worked. Ulysses passed over the solar poles through 3 separate campaigns, spanning nearly 2 complete solar cycles. It measured the fast polar wind directly. It mapped the magnetic field at high latitude. It ran for 18 years, 4 times its planned lifetime, and did not stop transmitting until June 2009, when the last of its heat faded and the fuel lines began to freeze. It never sent home a single photograph. Ulysses had no camera, not a broken one, none at all. It was conceived in the 1970s and built in the 1980s, when the instruments that mattered for this mission were particle detectors and magnetometers, and when carrying an imager that far out was mass nobody could justify. So for 18 years, the only machine ever to fly above the poles of our star sat in the one place in the solar system nobody had ever been, and felt its way around in the dark, sensing the particles, reading the field, like a person mapping an unfamiliar room with nothing but their hands, and no way to ever describe the view. We got there, and we still could not see. The second witness is at work right now as you watch. It is called Solar Orbiter, launched in February 2020, and it took the slower road. Rather than one violent throw past Jupiter, it has spent years in a resonant dance with Venus, passing close to the planet again and again, each encounter tilting its orbit a fraction further out of the plane. Not one shove, dozens of small ones over years. Its project scientist calls it the Stairway to Heaven. By February 2025, that patience had carried it to 17 degrees above the solar equator, more than double the angle of any sun-watching mission before it. And on the 23rd of March 2025, for the first time in the history of our species, we photographed the pole of a star. What came back was not what anyone had drawn. The textbook sun has a tidy magnetic geometry, a north and a south, arranged the way the ends of a bar magnet are arranged. The South Pole, seen directly, was chaos. North and south polarities scrambled together across the same region, a twisted, disordered magnetic landscape with almost no resemblance to the well-behaved surface we had been looking at edge-on for 4 centuries. The timing was extraordinary luck. Solar Orbiter arrived at high latitude precisely while the field was mid-reversal. It caught the flip in progress. The first proper look at the poles of the sun happened to land in the exact years the poles were turning themselves inside out. And it is not finished. On the 24th of December this year, Solar Orbiter passes Venus again, and that encounter lifts it to 24 degrees. That flyby formally begins what the mission calls its high latitude phase. Later passes take it to 33. But the sun is not the only thing hiding along the vertical. There is a larger question about the shape of everything we live inside. The sun blows out a continuous wind of charged particles, and that wind inflates an enormous bubble around the entire solar system, the heliosphere. Every planet sails inside it. It is not decoration, it is a shield, deflecting much of the cosmic radiation streaming through the galaxy. For roughly 70 years, we drew it as a comet, a rounded nose facing the direction of travel, and a long tail streaming out behind as the sun moves through the Milky Way. It was reasonable, it was elegant, and it is in every textbook. It may be wrong. Competing models now give it competing shapes. One school keeps the long comet tail. Another proposes a short, split, double-lobed structure that researchers describe, not entirely seriously, as a croissant. A third suggests essentially no tail at all. These are not fringe positions. It is an active, unresolved argument running in the literature right now. And the reason we cannot settle it is the reason for everything else in this film. We have never been outside it, looking back. The Voyagers did cross the boundary, both of them, but they left through the edges out along the plane, the same way everything else leaves. Neither ever climbed high enough to turn round and photograph the structure from above. We are trying to describe the shape of a house while looking through the keyhole of its front door. But something changed this year. In September 2025, a spacecraft called IMAP launched towards the point where the sun's pull and Earth's balance, reaching it in January and beginning its primary science mission on the 1st of February 2026. IMAP cannot go up either. What it can do is map the boundary indirectly, catching neutral atoms thrown back from the edge of the bubble and building a picture of a shape from the particles it returns. 6 months of that data now exist. For the first time, the argument has a referee. So how would you actually climb? If you cannot build a rocket with infinite fuel, how do you defeat 30 kilometers per second? The answer trajectory specialists give is so counterintuitive it sounds like a joke. It relies on something called the Oberth effect, and it demands the exact opposite of instinct. Instead of pointing upward and fighting, you aim at the sun and let go. As the spacecraft falls inward, it accelerates enormously, the sun's gravity doing the work. At the closest point of that fall, what astronomers call perihelion, it is moving faster than it will ever move again. And it is precisely there, at maximum speed, deepest in the gravity well, that you fire the engines. The principle was worked out by Hermann Oberth in 1929, and it is genuinely strange. The same fuel, burned at high speed inside a strong gravitational field, yields far more useful energy than it would anywhere else. It is the difference between pushing a swing at the top of its arc and pushing it at the bottom. Identical effort, enormously different result. Burned at perihelion, that fuel can finally cancel the sideways motion the cloud gave us and turn the spacecraft upward. The dive into the fire becomes the ramp out of the plane. There is a second approach, slower and stranger. Solar sails, sheets of reflective film, kilometers across, thin as smoke, pushed by the pressure of sunlight itself. The force is absurdly small, but it never stops, and given years, it can tilt an orbit no chemical rocket could afford to touch. Many engineers think the answer is both: a sail to climb patiently, and an Oberth burn for the final throw. So suppose we manage it. Suppose something of ours finally rises. What would it see? The first surprise would be the cleanliness. The plane we live in is dusty. Billions of years of collisions have left a thin veil of debris through the whole disk, faintly visible from your own garden on a dark night. A spacecraft climbing vertically would leave that haze behind within months, into space that is simply clearer. An extraordinary place to put a telescope hunting for life around other stars. The second would be the sun without disguise, the clean, fast polar wind at its source, the star seen finally from the angle it has been hiding. And the third would be the photograph, looking down for the first time on the entire solar system as a disk, the orbits drawn as circles, the dust rings lit from above, and in the background, the true outline of the bubble we live inside, settled at last. We have photographed the Earth as a pale dot from beyond Neptune. We have seen the far side of the moon, but we have never once looked at our home from above it. That is the portrait still missing from the album. And it is missing not because it is far away. It is not far away at all. But because 4.5 billion years ago, a cloud of gas happened to be turning. Everything we have ever built is still obeying that spin. On Christmas Eve, a small European spacecraft will pass Venus and tilt a few degrees further out of the plane. It is not a dramatic moment. Nobody will be watching. But it is the beginning of the answer, and it is the first time our species has ever seriously tried to leave the record it was pressed into.